Have you ever wondered how airplanes manage to fly, even though they are these massive metal structures? Of course, many different factors make an aircraft fly: aerodynamics, engines, control systems, but one of the constant challenges in aeronautics is weight. The lighter a structure can be made, without losing strength or stability, the more efficient and economical the aircraft becomes. This project looks at one small but important part of that problem: reinforced plate structures, thin metal panels used in fuselage skin, floor structures, and stiffened panels. Because these plates are so slender, they need longitudinal reinforcements, called stringers, to prevent buckling and to transfer loads to the main frame. These reinforcements can be attached in several ways, for example with rivets, or using friction stir welding, a solid-state process where a rotating tool stirs the material without melting it. The way we choose the stiffener layout and the joining method has a strong effect on how the structure carries load. In this project, a published scientific study was taken as a starting point, and its reinforced plate configurations were recreated and extended using 3D modeling and finite element simulations in SolidWorks and Abacus. Several families of models were analyzed: plates with 2 and 3 stiffeners, different stiffener shapes, including additional I and J-shaped reinforcements, and versions with and without a heat-affected zone. To understand not only the physics, but also the numerical model itself, a mesh convergence study was performed using 3 mesh levels, and the boundary conditions from the article were decomposed into separate cases so their influence on the response could be isolated. Looking at the results, 3 main messages emerge. First, the mesh study showed that as the mesh was refined, the predicted reaction forces tended to decrease slightly and stabilize, which helped to choose a mesh that is detailed enough, without making the simulations impractically slow. Second, comparing the different boundary condition cases revealed that changing how the plate is supported can significantly alter the maximum load and the shape of the force displacement curve, especially around buckling. Third, when comparing all reinforcement types and all load levels, a clear physical trend appears: introducing a heat-affected zone around the weld generally reduces the maximum load the plate can carry. And different stiffener profiles change both the weight and the mechanical performance. Some layouts give similar stiffness with less material, while others increase local stresses in the weld region and lower the capacity. In simple terms, the study shows that how you reinforce and how you join a thin aeronautical plate really matters. By carefully choosing the stiffener geometry, the joint type, and by modeling effects like the heat-affected zone, it is possible to keep the structure safe while reducing weight and avoiding overly optimistic numerical predictions. This project is a small contribution in that direction, helping to understand which design and modeling choices have the biggest impact when designing lighter and more efficient aircraft structures.